Hello and welcome. The purpose of this video is to go through this Born-Haber cycle for sodium oxide to be a nice reference for you as you're working through Born-Haber cycle. So sodium oxide, they give it to us in this diagram. We have a diagram of lattice enthalpy. They're asking us to calculate some values. They give us some values, want us to calculate values, and then find lattice enthalpy. Lattice enthalpy, that's the whole point of Haber, excuse me. Lattice enthalpy, the enthalpy to get to dissociate into ions, that's ultimately what we're trying to find. All right, so I'm going to start a process like this by labeling the Born-Haber cycle that they give me. I'm going to try to figure out what do each of these arrows show me. So first I see an arrow going from sodium and oxygen to form sodium oxide. Well, that is delta H of formation of sodium oxide. This is where we really need to know those definitions that we went over in HL time. The definitions of enthalpy, some of them, of course, not just from HL time, some of them from other topics even, but forming a compound that's delta H of formation. Great. So now, what do I see happening between this step and this step? Well, what I see happening is sodium going from a solid to a gas. So that's delta H. Which of your enthalpies is forming a gaseous element? That's delta H of atomization. Delta H of atomization for sodium. Notice it was only sodium that did atomization or changed to a gas in that step. Okay. And they actually give us that value, and they give it to us right here. So let me do that in a different color. This is 107 kilojoules per mole. Awesome. All right, what happens here? Well, again, I have something changing from 1/2 O2 to oxygen gas. That's the only change that happens from this step here to this step here. Well, again, if I'm forming 1 mole of gaseous atoms, which of those definitions is that? Forming 1 mole of gaseous atoms. If you're not sure, pause the video, go look it up. I just formed 1 mole of gaseous atoms from 1/2 O2 to form here 1 mole of gaseous atoms. Again, delta H of atomization. That's the definition of delta H of atomization, enthalpy change of atomization, this time for oxygen. And lucky me, the IB was so kind to me, it gave me that number. Beautiful, beautiful, beautiful. All right, we have another jump here, this time from 1 mole of gaseous atoms. And the thing that changes is actually, oh, sorry, it's actually sodium. I got ahead of myself. We have some sodium. Sodium changes to have a charge. Well, what's that? Sodium going from sodium to sodium plus 1. What is that? That's ionization energy. We learned about that way back when in year 1, the definition of ionization energy, the energy required to remove 1 mole of electrons to form 1 mole of gaseous atoms, which of course gives you a positively charged thing. So if I see sodium going from sodium to sodium plus 1, that's ionization energy, and ionization energy, of course, for sodium. Now, the next step, what's the thing that changes between the steps? Oxygen gas becomes oxygen 2 minus gas. What happened here? How do we form negative ions? Which of the energies is that? That's not enthalpy, gosh, electron affinity. Electron affinity, the energy released when 1 mole of electrons are added, but it's electron affinity 1. And notice I got to 2 minus, so also electron affinity 2. I had to add electrons 2 times, right? I needed to add 2 electrons per oxygen in order to get to 2 minus. I'll let that sink in and say it one more time. In order to go from oxygen to oxygen 1 minus, well, that's our first electron affinity, adding 1 mole of electrons to 1 mole of oxygen atoms. But now I'm only at 1 minus. So to go from oxygen 1 minus to oxygen 2 minus, that's my second electron affinity. I needed to add yet another mole of electrons to the thing that was already a -1 charge in order to get to oxygen 2 minus. All right, so hopefully that helps. I think it's pretty straightforward now to do our finds. So to go from 1/2 oxygen to O2 minus, I'm just going to find those. Here, to go from 1/2 oxygen gas, that's the same thing I see here, to O2 minus. Well, what are all the oxygen things that got me from this step here to this step here? Let's see. I have delta H of atomic atomization. That was one of the oxygen things. And then I also had the electron affinities for oxygen. Those were the only steps in this process that involved oxygen, right? Because the other steps I had involved sodium. So this is going to be the delta H of atomization of oxygen, which is just 107 kilojoules per mole, plus, where do I find these two electron affinities? You'll notice I already had my data booklet open. Not an accident. Electron affinities, I actually can't write on this, but notice you have first and second electron affinities, which is awesome. My first and second electron affinities for oxygen are, pay attention to signs, please, -141 kilojoules per mole plus 753 kilojoules per mole. And the answer you should come up with here is, let me double check, 861 kilojoules per mole. Pay attention to signs. Notice that all of these arrows are going in the same direction, so I'm adding, but in this case I had to add a negative thing, and so ultimately that's subtracting. Yes? Okay. What about sodium? How did I get from sodium solid to sodium plus 1? Excellent question. I'm asking myself the same thing. Well, let's look at which steps involve sodium. Delta H atomization of sodium and ionization energy of sodium. Delta H of atomization of sodium I have right here, 107 kilojoules per mole, plus ionization energy of sodium. Well, luckily the same chart has first ionization energy. It is indeed the first ionization energy because I only got to sodium plus 1, so that's perfect. So first ionization energy of sodium I have right here. Let's look it up. It should be in the top left corner. 496 kilojoules per mole. Beautiful. And the answer you should get there is 603 kilojoules per mole. All right. So I'm actually just going to erase what we have here. You can go back in the video if that's helpful to see that annotation again. Okay. So now I've done part A. The second part, they give me a standard enthalpy of formation. Oh, well, if I remember from my labeling, this was delta H of formation. So now I know it's equal to -414 kilojoules per mole. And now I need to find lattice enthalpy. So that's going from Na2O, sodium oxide, to my ions. That's lattice enthalpy. Using section 8 of the data booklet. So section 8 of the data booklet, we kind of already used in here. So we don't actually really need to use it again because we can see we already have here the numbers we'll need. All right, so I know that together to go from here to here is 861 kilojoules per mole from sodium plus 861 plus 603 kilojoules per mole. But notice sodium, you need 2 sodiums for every one to form 1 mole of sodium oxide. So 2 sodiums I account for just like that. All right, and now this arrow is going in the other direction. Awesome. So that means I'm going to subtract my delta H of formation. So to go from here to here, I'm adding all of these arrows, subtracting out this arrow because it's in the opposite direction. So your math is going to be 861 kilojoules per mole plus 2 times 603 kilojoules per mole. And those are the numbers we found to get you from this step to this step. To account for that entire diagram, I'm then going to subtract this step, subtract negative 414 kilojoules per mole. Notice you really have to pay attention to signs here. You're subtracting a negative, and that should be equal to, if you've done all of your math correctly, 2,481 kilojoules per mole. And now we should feel happy because we understand how to do a Born-Haber cycle for sodium oxide. Questions, thoughts, concerns, comments, ideas, anything you want to say, send me an email, add it to the homework document, and enjoy. It's kind of fun at the end, right? It all just came together.